one thing that vectors are often used for is to represent motion. So if we have the position vector of a particle, and then we have a second particle's equation for the position vector, then, at any given time t, then two things can occur. The paths can cross, so we can have a point of intersection. Or they can collide, which means that the paths cross at the same time. We want to describe that as a vector. So the velocity of particle 1 is 2 meters per second. Sorry, I haven't said it here, but let's go with position as being meters. For particle 2, its velocity is -1, -2 meters per second. Okay, why? Because if t is 1, so the space of 1 hour, and we substitute that into there, then the direction vector tells us how far they've moved in the space of an hour. The speed is calculated a little differently, and it's the magnitude of the velocity vector. It's important that we leave velocity as a vector because what we're dealing with is direction anywhere in 360 degrees. You could convert that velocity, say 2, into a bearing, okay? Speed in that direction on that bearing, but you're not required to do that. It's perfectly acceptable to represent velocity as a vector in this context. So the speed is the magnitude. Make sure you got brackets around your negatives there, is √5 meters per second. Okay, so velocity and speed, very different things, particularly in the context of vector equations. So, will the paths of the particles cross? Let's assume for a minute that these are different. So, if we extract the equations, we can solve these simultaneously and determine whether or not these vector equations intersect. So, by doing equation 1 minus equation 2, we get 0 equal to -1 equal to, plus t2. So t2 is 1. And if I substitute that back into each one, then I get 2t1 equals 4 minus 1. So t1 is 3/2. And checking the second equation, 2t1 is equal to 5 minus 2 times 1, which is 3/2. So will the paths cross? They will. Okay, there is a parameter for each equation where the position vector will be the same, and we could work that out. The paths may cross at different times. So there may be a point at which the paths cross, but there may not be a time. To determine whether there is a time that they cross, we go back to t being the same. Okay, the assumption that the particles begin moving at the same time. And if we then look at solving that for each component, then at 4/3 of a second, the I components will be the same. And at 5/4 of a second, the J components will be the same. And because they are different, that means that they will not collide. So while the paths of these particles do intersect, it does not happen at the same time. And that's illustrated here. The blue line is R1. The pink line is R2. This is the x-axis, that's the y-axis. So what we have happening is this point of intersection, which we could have calculated at 3,3, but particle 1 gets there at 4/3 of a second, particle 2 gets there, particle 2's moving that way, particle 1's moving that way, particle 2 gets there at 5/4 of a second. So there will be no collision because they're at that point at different times.